All right, section 6.2, representations of functions. We did a little bit of this yesterday. I've got some more problems for us to look at to review our area formulas, nope, never mind, that's tomorrow, never mind, our area formulas. It says, complete the mapping diagram for the area of each figure and then write an equation that describes that function. Weird. Okay, so we have a triangle here. It says when you input 1 or 2 or 3 or 4, it wants to know what the output is. So when you input 1, we're actually plugging that in for what part of the triangle? What would we call that length from the base to the bottom of the triangle here? What is that, Brady? Height. That's the height. Yeah, so X is just the height of the triangle. What is the base of the triangle? Sky? 4. It's 4. Yeah, it's 4. So the function we could write for that, the equation or the function that we could write for that rule is we could say, well, you're going to do 1/2 times 4 for the base, because remember the triangle formula is 1/2 base times height. And then we're going to plug in X for the height. And all of that is going to equal the area. So on the other side of my equation, there's my A equals. Now we can simplify that a little bit. What's 1/2 of 4? 2. Yeah, so why don't we just say, I'll put this over here, A equals 2X. Now that is the area of this triangle. Not every triangle is going to have a base of 4, so this only works if your base is 4. If you plug in 1, what would that make the area of your triangle? Here, 2. If you plug in 2, that'd make the area, everybody, 4. If you plug in 3, that'd make the area, and if you plug in 4, 8. All right. Again, that's for this triangle. Is this a function? Is every input pointing to an output? Okay, this is a function then. Is it a linear function? If I were to replace this A with a Y, is Y equals 2X a linear function? Yeah, it is. It has a slope of 2 and it has a Y-intercept of 0. Yeah, it starts at the origin. Because again, if I don't have a height, I don't have a shape at all. There's no area. Okay. So that's linear. B, we've got, what shape is this here? For example, B. What is that, Deegan? It's a trapezoid. And Deegan, do you happen to remember the formula for the area of a trapezoid? Okay, times the height. There's one extra thing. Okay. Yep. 1/2 B1 plus B2 times H. It's actually the triangle formula with another base. So triangle formula, 1/2 base times height. Trapezoid formula, 1/2 bases times height. I add those two bases, and on a trapezoid, there's 2 sets. Sorry, not 2 sets. There are 2 parallel lines. There's actually one set of parallel lines, and those parallel lines are the bases. The height of the trapezoid is going to connect those bases at a right angle, which makes the height of this trapezoid 2 and not whatever that is. That slanted height is not what we're looking for. Of course, we've done enough volume and surface area to know that the height always connects bases at a right angle. So when I plug in for X, that's going to give me, let's just say that base 1 is X and base 2 is 2X, because that's what I'm seeing here for the bases there. We'll say the height is 2. See if we can simplify this up a little bit to get our function rule. Jace, what's X plus 2X? Okay. And Emerson, what's 1/2 of 2? Yeah, so really, our function can be simplified all the way to A equals 3X. So when you plug in 1 for X, what's A going to be? What's the area? 3. For this trapezoid, it's 3. What about when I plug in 2? Everybody? 6 when I plug in 3? When I plug in 4? 12. Is this function linear? Yes, just like the last one. Has a slightly larger slope, slope of 3. You can tell it's linear because every time the output or the y value rises by 2, the run is 1. Rise 2, run 1, rise 2, run 1. That's always going to make a line because lines have constant slopes. Rise 3, run 1, rise 3, run 1, rise 3, run 1. That's going to give you a line. The fact that this number is 3 times this number, that also tells you that it's a line. But if that doesn't happen, so next chapter we're going to talk about the Pythagorean theorem, and then there's also something called the Converse Pythagorean theorem. When you flip a statement around, it doesn't always make it true. Okay, it doesn't always make it true. And so if I were to tell you that if this number is a multiple of that number, if there's a constant number that's being multiplied to all these, that's just going to tell you that it's a direct variation, which is a line. All direct variations are lines. Flip it around. Are all lines direct variations? No, that's not true. So you have to check using this method. But if you have an obvious direct variation, you know it's going to be a line then. It just doesn't work the other way around. Here's another example of that. Are all squares rectangles? Yes. By definition, a rectangle is a quadrilateral that's also a parallelogram, 2 sides that are parallel and congruent with right angles. Does a square have congruent opposite sides and right angles? So it's a rectangle. It's just got all equal sides, right? All congruent sides. So every square is a rectangle. Is every rectangle a square? No. So I can't flip it around. Every square is a quadrilateral. Is every quadrilateral a square? No. So just because I reverse something around doesn't make it true. So if I see a direct variation, it tells me it's a line. But just because it's not a direct variation doesn't mean it still can't be a line. All right, so our vocab word for today, a function rule is an equation that describes the relationship between inputs. Now, remember the inputs was the independent variable. So it describes the relationship between the inputs and then the outputs. The outputs was the y or the dependent variable. Change this color. All right, so the inputs, that is the x variable. The outputs is the y variable, the output is. And so this is a function rule. It's just simply an equation. Like the last one we had was y equals 3x. So when we plug in -2, it's going to input -2, we output -6. If we input 7, we're going to output 21. Okay. I like to think of functions, and they're just equations, but I like to think of this, I think it's called, is it the pack-a-punch machine? For those of you who play the Nazi zombies? When you input a gun and it upgrades it and puts it back out, you know what I'm talking about? See, Nazi zombies was a lot popular like when I first started teaching this subject. So I don't know how many people actually still play it, but there was a pack-a-punch machine. And so when you could just upgrade your guns. And you knew if you put in this gun, it was going to upgrade it and give you this back. You didn't put in the pistol and all of a sudden get a rocket launcher back, right? That was like, oh, wow, that was crazy. That would not be a function because then I input something and it gives me one output and then I get another output and we know that wouldn't make a function at all if that was the case. So let's write function rules based off of these sentences here. See if we can do that. The first one says the output is 5 less than the input. How could I write that as an equation in slope-intercept form? Maddox. Perfect. Y equals the output is means equals, output y is means equals 5 less than. I'm subtracting 5 from x. The common mistake I see with subtraction is when you read it like this, I have a lot of students put 5 minus x. That means x less than 5. 5 less than x means I start with x and then subtract 5 from that. What about the output of the square? Sorry, the output is the square of the input. Christian? Perfect. And the last one, the output is 8 less than twice the input. Jimmy? Perfect. What if I told you that one of those was not linear? They're all functions. Which one would you say is the non-linear one? Xander?
Y equals x squared.
Yes. If I'm squaring my exponent, it is not going to be linear. And we'll look at that in just a moment, and I'll show you why. We talked about that earlier in the year. We said that if the x has an exponent other than just being, just an exponent of 1, maybe, it's not going to be linear. So that means to the third power, fourth power, fifth power, half power, third power, none of those are going to be linear. However, A and C are both linear. Okay, so let's compare A and C. Between function A and function C, which one has the greater slope? Jacoby? C, yeah, we're comparing slopes, a slope of 1 versus a slope of 2. Okay. Which one of them has the greater y-intercept? Sky? Yeah, -5 is actually bigger than -8. That's correct. All right. And could you graph those? Because you did on your homework that's due today, so hopefully. Okay. Next one. Whoa. Okay, we're not going to work with a partner today. Make a table that shows the pattern for the area where the input is the figure number x, so figure 1, figure 2, figure 3, figure 4, and the output is the area, meaning the number of squares. Write an equation that describes the function, and then use your equation to find which figure has an area of 81 when your pattern continues. We'll see if we have time for that. Let's look at A. For figure 1, the area is 1. For figure 2, the area is 3. For figure 3, the area is 5. For figure 4, the area is 7. I probably could have put those numbers. I'd like to line them up, but I don't think I'm going to be able to line them up unless I put it on the bottom. But then that intrudes into part B, so I'm not going to do that. Whoa, stop doing that. 3 there, 5 there. Why do I bother? Okay. So it says, see if you can write an equation. What do you guys think? Can we have an equation for this?
Y equals x plus 2.
Y equals x plus 2. Why do you say x plus 2? Because it's increasing by 2 each time? Does that mean y equals x plus 2?
Probably not.
Let's try it. Probably not, but because my tone of voice says no.
Yeah.
Let's try it. According to this equation, for figure 3, my area should be 5. Okay. For figure 4, my area should be 6, but it's 7. Okay, so that doesn't work. It works for figure 5. For figure 2, if I plug in 2 for figure 2, the area would have been 4. Again, so it only works for this one here. Okay, so that's we want one that works for everything. So it's not y equals x plus 2. The number of squares is increasing by 2 each time. That doesn't mean we want our y-intercept to be 2. That means we want our rate of change to be 2. What's another word for rate of change? Julia? Slope, yeah. So let's move the 2 over in front of the x. Okay. Now it's still not complete because for figure 1, if I plug 1 in, that should give me an area of 2, and I'm not seeing that. So what do I have to do now? Sky? Subtract 1. Let's see if this works. If I plug in for 1 for figure, if I plug in x equals 1, I should have an area of 1. If I plug in x equals 2, I should have an area of 2 times 2 is 4 minus 1 is 3. That's too good for 2 of them. If I plug in 3, 6 minus 1 is 5. Okay, I think I found an equation I can work with. Y equals 2x minus 1. Is that linear? It's linear. The slope's constant. you're always increasing by 2 all the way through. The next shape is going to go from 7 to 9, then 9 to 11. I can always predict. What about the next one? Figure 1 has an area of 1. Figure 2 has an area of 4. Figure 3 has an area of 9. Figure 4 has an area of, it looks like they're just adding a row on each time. And so it's 9 plus 7, which is 16. Okay. So what function rule can we write for this one? You shut the door for me, Shane. What do you think, Lizzie? Y equals 3x minus 2. Let's try it. If I plug in 1, 3 minus 2 is 1. Works for the first one. If I plug in 2, 6 minus 2 is 4. Works for the second one. If I plug in 3, 9 minus 2 is 7. Okay, it doesn't work for the third one. So what we need to do is we need to think outside of the realm of linear equations. Because if I look at any 2 figures, I can make it work for 2 of them. I just can't make it work for all of them. So think outside. This is not linear. What do you think, Brady? I think it is right. I think when you plug in 1 and you square 1, you get 1. When you plug in 2 for figure 2 and you square it, you get 4. You square figure 3, you get 9. You square 4, you get 16. This is y equals x squared. This is the same function that we wrote up here, but a visual representation of what that actually looks like with squares. 1 squared, 2 squared, 3 squared, 4 squared. What's figure 5 going to have? How many squares is it going to have, Sky? 25. So I don't mean to say that you can't predict. I think I said that you can't predict, or I said you could predict if it's linear. You can still predict if it's nonlinear, but what we're going to see is that rate of change is always varying. It's a variable rate of change. It's not constant like the lines are. So if I graph this, it's going to curve. In fact, the rate that it's increasing is increasing. We increased by 3, we increased by 5, we increased by 7. The next one's going to increase by 9. It's just going to keep increasing at a faster and faster rate. And that's why instead of a line, this is going to start making a curve. And it's going to look like that. It's going to increase faster and faster. It says, then use your equation to find which figure has an area of 81 if the pattern continues. So if I'm looking for 81, let's do the nonlinear one first. What figure is going to give me an area of 81? Jimmy? Figure 9. Okay. So essentially what I'm doing is I'm plugging in 81 for y and then asking what number squared, or the square root of 81, which is 9. What about for the linear one up above? Do the same thing. You're like, oh, it's going to be complicated. I'm going to have to count all the, no, you don't have to count anything. If you want its area to be 81, then plug in 81. Solve that. Add 1 to both sides. Sorry, I think I did a combo of 8 and 2. What's x going to be, Jimmy? 41. Figure 41. It's going to take you a lot longer to get to an area of 81 with this linear function, where it just increases by 2 every time, than this exponential function, which increases by, well, a varying rate each time because you're squaring the number. Okay. Speaking of plugging in numbers, it's exactly what we're going to do here for this next one. Evaluate each function with a given value of x. They give us a linear function, y equals 2x plus 5. They want you to tell what y is equal to when you plug in 3. Now, when you plug in a number for x, you're inputting it. Remember, the x is the input variable. So I want to know what the output is. When you input 3, what's it going to output? Christian? 11. Now, 6 plus 5, it's going to output 11. I guess I could put y equals if you wanted to, because that's the output. Y equals 11. What about, for example, b? if you input a -1, be careful here. There's a place you could make a mistake. The negative that's in front of the x is still there. When you input the -1, it just puts the -1 in for the x. What's -1 squared? Xander? 1. And what's negative times 1? -1. Yeah, so this one's going to output a -1. When you square a number, it's always going to be positive. Because if you have a positive times a positive, or if you have a negative times a negative, it's still going to make a positive. But when you have a negative in front of the square that you can't control, which this one does, then it's going to reverse it back to negative. So this one should output us a -1. So input -1, output -1. That means the point -1, -1 is somewhere on that curve. And I know it curves because it's not linear. It's got the exponent squared. Okay. All right. Function rules can also be written as f of x, and they read f of x. Okay, so you'll see that next year a little bit more often than what you are this year. I'll write it occasionally, but you'll see it a lot next year. So x is the input. F of x is the output, or the y variable. So we're replacing y with f of x. And so let's try to do this again. And so the reason people write it like this, you can see in that second example for D. The reason people write it this way is because it actually tells you what you're inputting without having to write it off to the side. This one says f of x equals 3x minus 7, x equals 5. Okay, so we have to figure out what f of x is when I input 5. This one says f of -2. Automatically tells me I'm going to be inputting -2 in for x. And figure out what the output is. Let's do example C first. When you input 5, you could say f of 5 equals 3, and then plug it all in. Martin, what's that going to give you for the output? 8. So f of 5 is 8. When I plug in 5, I get 8. That's what that means. When I plug in 5 for my function, I get 8. This one, when I plug in -2, f of -2 is going to be -3 times -2 cubed plus -2 squared. This one kicks up the difficulty level a notch or 2. What's -2 cubed? You're thinking -2 times -2 times -2. Connor, thanks for volunteering. -2 times -2 times -2. -8, that is right. While you're at it, go down a notch. What's -2 times -2? +4. Excellent. Okay, so we've simplified this quite a bit. Emerson, take it from there. What's -3 times -8? Okay, and what's 24 plus 4? So when I input -2, f of -2 is going to give me 28. That's how I could write that. And so that's literally the coordinate point, -2, 28. I know for sure that that's somewhere on this mess of a graph. A function rule can also be represented by an input-output table and by a graph. We looked at the input-output tables yesterday, even with the mapping diagrams. So if I wanted to write this in slope-intercept form, can someone tell me, either by looking at the graph, the chart, or by the graph, what the slope of that line is? Owen? 1. Okay, so y equals, but y is going to get replaced with f of x if I'm talking about a function. F of x equals 1x, or just x. And then, Owen, what's the y-intercept? 2. So if you look at the graph, you can clearly see the y-intercept's 2. If you're looking at the chart over here, you're going to have to work down and see what y is when x is 0, because x is 0 is the y-axis. So if I go down 1 and then go down 1 there, because the slope's 1, that's going to tell me that 0, 2 is on my graph, and that's what Owen said the y-intercept is. All right. Now we're going to compare 3 different functions. We're going to compare for function A, y equals, or f of x equals -2x plus 1. Oliver, where do I start? Where's my y-intercept for the graph of A? 1, okay. And what's the slope? And that tells me to do what from this point? Yeah, down how many? Okay. Good. Yeah. Remember, -2 as a fraction, since slope is rise over run, -2 could be -2 over 1. And so I could also go up to left 1. Either way, you're going to end up on this line. So this green line right here represents the function for A. And as you probably guessed, it's linear because it's in slope-intercept form. Of course, it's going to be linear. The function for B is not going to be linear because we have the exponent 2 next to our x. So what I'm going to do is I'm going to have us graph 5 points to see what happens with this curve. The points I'm going to have you use are, well, one of them is going to be 0. That's all. Do you remember when we first learned about linear equations? I had you plug in like 0, -1, and 1. You had to plug in, and if they all 3 lined up, you knew you did it right because there's going to be a line. Well, with the curve, I really do have to do that. And so I'm going to have you graph -2 for x. We're going to input -2. We're going to input -1. We're going to input 0. We're going to input +1, and we're going to input +2. And why did I make those red? I clearly could have made the purple. And I'm off my game today. Okay. So when I plug in -2, what's -2 squared? Carson? 4. Now make it negative. What's -4 plus 1? -3. Now the reason I'm having her make it negative because that negative right there is out of my control. I'm squaring the number I'm putting in, then making it negative. Because squaring a number is always going to make it positive. A negative in front is always then going to make it negative. So if I plug in -1, what's -1 squared? -1 times -1. 1. 1 plus 1. 2. Oh, sorry. 1, make it negative first. -1 plus 2. What'd you say? -1 plus 2, or -1 plus 1 is 0. I can't talk, so you said the right thing. 0. If I plug in 0, 0 squared, of course, is 0. -0 doesn't exist. What's 0 plus 1? Thank you. 1. Now, if I plug in +1, I'm actually going to get the same answer as when I plugged in -1. Plugging in +1 is not going to matter, so it's still going to get 1, make it negative, add 1, and it's now 0. If I plug in +2, I'm going to get the same answer that I got when I plugged in -2, because +2 squared is still 4, just like -2 squared was 4. Make it negative, -4 plus 1 is -3. So when I go to graph these points, -2, 3, -1, 0, 0, 1, 1, 0, and 2, -3 do this. And so what we have here, I know it kind of looks like a V. It's not. It's called a parabola. And you'll look at a lot of these next year. That's a bad one. This particular parabola has been inverted to point. Why can I not get this to go right? Yeah, it's a little better. It's been inverted. It's opening down. You'll also learn why it's opening down. I'll give you a hint. It's because there's a negative in front of the x squared. Typically, parabolas look like this, but when you put a negative in front of them, they look like this now. Just like most lines look like this, but if you put a negative in front of it, the slope's negative. Now it looks like this. It's inverted. Okay. What about x to the third power? Let's plug in the same numbers. Let's input -2. Let's input -1, input 0, input 1, input 2, and see what happens. What's Connor? I think you said -2 cubed was -8, right? -8. Okay. What about -1 times -1 times -1 times -1? -1. Yeah, 3 negatives. -1 times -1 times 3 negatives will result in a negative. What about 0 times 0 times 0? Xander?
0.
0. 1 times 1 times 1? Everybody? Thank you, Seth. 1. And 2 times 2 times 2? 8. So interesting, when I cube a number, it doesn't have to be positive. It could be negative or positive. We'll talk more about that in a couple chapters. So -2, -8 is going to be somewhere in this area because it's off my graph. -1, -1 is here. 0, 0 is there. Then 1, 1 is here. It's a good thing I didn't just use the middle 3 points. I might have thought this was linear. And then 2, 8 is all the way off my graph up here. And so this one does one of these numbers. And that's what all x to the third power functions will look like. Some sort of, it's not a parabola because it actually goes in both directions, but it's definitely not a line. Okay, so only one of those is linear. And what makes it linear is the fact that there's no exponent with the x. The other two are nonlinear. You got a 50 today? 45. Okay. All right. The number of pounds P of carbon dioxide. What's the molecular formula for carbon dioxide? Owen? CO2. Good. Carbon dioxide. The number of pounds P of carbon dioxide produced by a car is 20 times the number of gallons G of gasoline used by the car. Write a graph of a function. Write and graph a function that describes the relationship between G and P. G being the gallons of gasoline and P being the pounds of carbon dioxide. So here I'll say it again. The pounds is 20 times the gallons. If I use P for pounds and G for gallons, what's an equation I could write that represents that particular sentence? The pounds is 20 times the gallons. I should see more than 2 hands up in the air. It's the same ones I'm always seeing. Give it a shot, Dawson. Yes, I'm going to do G equals, but no, wait, hold on. Say it again. How about 20 G equals P? So P equals 20 G. It says the pounds P, then it says is, there's your equal sign, 20 times G. So take the number of gallons your car is using, times it by 20, and that's the pounds of CO2. CO2 is a gas, so that would be heavy, right? This pounds of CO2. And so it wants us to write the equation, and it wants us to graph the equation. And let's start with the slope or the y-intercept. Jacoby, what's the y-intercept of that equation? It would be. If I don't use any gallons, I'm not going to produce any carbon dioxide. So we can start here at 0, and then I want you to use your slope to graph the line. Hello? I do. All right, I'll send her now. Bye. Your mom's here for pickup. So my slope's 20. Do I rise 20 and run 20? That'd be a slope of 1. I rise 20 and I run 1. And I'm going to have something that looks like this. And yes, that's a direct variation because the y-intercept we set is 0. Got everything? All right. See you tomorrow, Lucy. So we can write a function from an equation. We can write it from a table. We can write it from words. We can write it from more tables, I guess. So now it says write an equation that describes the function. Let's see if this is linear or not. What am I rising by? Maddox? -2. And when I rise -2, which means go down 2, what am I running by, Maddox? 2. If that's constant all the way through, then I have a line. Down -2, down -2, up 2. I guess I could put plus. Up 2. This is a line. Not only that, but you just found your slope. If your rise is -2 and your run is 2, what's that reduced to, Maddox, for a slope? -1. Remember, slope is the change in y over the change in x. You're going to get this wrong if you do the x first. Make sure you put the y, the rise on top. Okay. Do we know what the y-intercept is? The y-intercept is when x is 0. Do they give us x being 0? They don't. So I have to think about it. They give us y equals 0, but that's the x-intercept. I don't care about the x-intercept. So I'm going to have to build this equation knowing the slope is -1, but I'm going to have to think back. So instead of going backwards down 2 and skipping over 0, why don't we just go down 1 and back it up 1, which is actually adding 1. That's the same. And that's going to take us to what? 0, comma, what's our output going to be, Jimmy? 1. And then so we're going to write our equation as -x plus 1. You're going to see that a lot of the stuff we're doing in this section and tomorrow's section are very similar to what we did on our linear equations chapter, because it's the same thing. All right, we'll stop there, and I guess we'll finish with that very last problem tomorrow. All right, we left off with example B. Again, and we were supposed to write an equation that describes the function. So with example A, we found the slope. We said the rise was decreasing 2, the run was increasing 2. And if you put rise over run, -2 over +2 gives you -1. Then we were able to, using just a little mental math, figure out what the y-intercept is. Of course, we know the y-intercept is the value we get for y when x is 0. Because the y-axis, all the x coordinates are 0. And so we had to work backwards a little bit, but we found out that it was going to be +1. So our equation in slope-intercept form was y equals -x, -1x, plus 1. Now we're going to do that for example B. For example B, we first start by finding our slope. Now the table is sideways, but it doesn't change what we're going to do. We're going to find the rise first. The rise is the x or y coordinates. I'm asking. It's not both. I'm asking. Maddox? Yes, it's for the y's, the rise over run, right? So change in y over change in x. So Maddox, what's the y changing by each time? 5. Add 5 or subtract 5? Okay, so the rise is +5 every time I move down this chart. The run is the x coordinate. The run is increasing 1 each time. So Carter Shannon, if I put rise over run, is that 5 over 1 or 1 over 5? 5 over 1, and what's 5 over 1 the same as? 5. Shane, thank you. You know what to do. So our m value, and again, we're writing these as y equals mx plus b. This is called slope-intercept form. You remember that from chapter 4 a while back ago. Our m is 5. Yes. I'm at the last example of our 6.2 notes from yesterday. We will be in just a minute. Now, the last example, we had to work backwards to try to find out what the y-intercept is. We don't have to do that here. Sky, what's our y-intercept? Where it crosses the y-axis. Not 4. Sorry, I saw you raising your hand. I thought you were going to ask me a question? No. No. It's when x equals 0. I'm so confused. The y-intercept is the point where it crosses the y-axis. And on the y-axis, if I draw a picture, it might help. On the y-axis, all the points on the y-axis have an x coordinate of 0. Do any of the points in our chart give us an x coordinate of 0? Yes. And what's the y coordinate when x is 0? So that's our y-intercept. Our b value is going to be 25. Okay. This time they gave it to you. Last time we had to work backwards because they didn't give us x being 0, but we had to, a little mental math. We could figure out that when x was 0, y was going to be 1. Again, that's given to us here. So now that we know our m is 5 and our b is 25, a chance for redemption here, Sky. What's the equation going to be in slope-intercept form? That's right. Y equals 5x plus 25. take the graph away and it can confuse you if you're not careful. But yes, it's going to cross at the y-axis at 25 up there. All right, so yesterday's lesson was titled Representations of Functions. We talked about 5 different ways that you can represent a function. You can represent it in words. Some of the problems we did yesterday, we had to change something into words, like an output is 2 more than its input. We could also write it as an equation by replacing output with y, input with x, y equals x plus 2. We could write it as a table, like the problems we just looked at, where they give us a bunch of x inputs and a bunch of y outputs, and all of these coordinate, these are 4 coordinate pairs. They're all on that line. I mean, you know, that right there is the y-intercept, and we know the y-intercept's 2, so that makes sense. Okay. We can also look at a mapping diagram. That tells us this is definitely a function, but it also gives us those 4 points. And the 5th way is by actually graphing it. And if you graph y equals x plus 2, it'll look like this. That's what you did on the homework that was due yesterday, was graphing those slope-intercept equations. And then there's this funny little comic strip I found in your textbook. So I graphed our profits, and then the cat says, think again. And says, I'm happy to say that they're going up every day. Why is the dog mistaken? Lizzie? The graph is sideways. If you tilt it the way it's supposed to go, you can actually see the profits are going down throughout the week. But yeah, I guess you can take data and you can misinterpret it, or you can present it any way you want to. So I guess one of the sections we'll do later, we're going to look at data and make sure it's not misleading. Because it's very easy to have misleading data and try to trick people based off of, not because the chart's sideways, but you can do other things to manipulate your data. All right, that's section 6.2. Can you go ahead and download 6.3? Yeah.